All right, everyone. I hope you can hear me all the way back. Welcome to the side channel sessions. In this session, we have four amazing papers, where each paper either defends against a microarchitectural side channel or shows a new way of exploiting microarchitectural side channels. Our first presenter is from University of Washington, Alexandra. To briefly introduce her, Alexandra is a second-year PhD student at the University of Washington. Her research focuses on programming languages and security, and particularly on applying formal methods towards building defenses for hardware security. Please join me welcoming our first presenter, Alexandra. Alexandra, the stage is yours.
Hey, thank you. I'm Alexandra Michael. As he said, I'm a PhD student at the University of Washington, and I'll be presenting our paper on avoiding instruction-centric microarchitectural timing channels via binary code transformations. So, as I'm sure you will all be hearing repeatedly at this conference, Moore's law is slowing down. And one consequence of that slowdown is that hardware vendors are exploring novel microarchitectural optimizations as one way to replace some of those performance gains. But these optimizations also create new vulnerabilities. Recent work has shown that many of them, both implemented and proposed, create side channels that leak private data from cryptographic code, even which has been written to be classically constant time. This is a problem, and in our work, we work to address this problem by building proactive software defenses against a class of these optimizations called instruction-centric optimizations. This is a class of microarchitectural optimization that speeds up in-flight instructions based on either properties of the instruction or its operands, such as operands having a special case value like 0, or both the property of the instruction and the hardware state, for example, checking whether an operand value matches the contents of memory at some address. So how is this dangerous? Let's look at an example. We have the subtract instruction, and we can imagine that we're subtracting by some cryptographic secret. And we have an attacker, some process running on the same machine, who wants to learn that secret. Now, normally this would execute about as you would expect. You calculate ECX minus EAX and store the result back into the ECX register. However, one type of instruction-centric optimization might recognize that, hey, if EAX is 0, I don't actually need to do all this work because the result is just going to be ECX. No calculation is needed to actually execute this instruction. However, this optimization creates a fast path on a system that implements it, and the attacker can detect that fast path and thereby learn whether or not EAX, our cryptographic secret, is 0. We refer to this as an instruction-centric timing channel. In this work, we look at two types of instruction-centric optimizations and the timing channels they create. First, computation simplification. This is a broad class of optimizations that speed up arithmetic operations when their operands have special values. The subtract instruction that we saw on the previous slide is one example of this, which can be optimized when its second operand is 0. Another example would be multiplication, which can be sped up when either of its operands are 0 or 1. Those of you familiar with zero-skip multiply might note that this is essentially a broader version of that. Our second type of optimization is called silent stores. This is a type of optimization that optimizes memory store operations when the value being stored matches whatever is already at that destination address. So in this example, we might leak secret data when either EBX or the address it's being stored to in ESP contains some cryptographic secret. Okay, so what do we do about all this? Our solution is called instruction-centric transforms. And the key idea here is that if we have a potentially leaky instruction, we can replace that one instruction with a sequence of different instructions, which we call a transform, and which we can formally verify to satisfy two properties. First, this new sequence is going to be semantically equivalent to the original instruction, meaning that it does the same thing and has its registers end in the same state as the original. Second, this new transform will be safe, meaning that it prevents any instruction in the new sequence from being subject to the classes of optimization that we consider. A quick note on this definition of safety. Ideally, safety would mean that there were no side channels whatsoever, but this is a really hard property to show because without knowing the microarchitecture, I'll remind you that these are software level defenses, we don't know what it might leak. And even if we did know the microarchitecture, vendors might not tell us what it leaks. So for purposes of this talk, when I say safety, what I mean is that the optimizations we look at can't be applied to instructions that are operating over secret data. All right, so what do these transforms look like in practice? Going back to our subtract example, our goal in transforming this instruction is to avoid the fast path where we might subtract by 0 and allow an attacker to determine some information about a cryptographic secret in EAX. To prevent this from being possible, we can start with the insight that currently this instruction is operating over only 32 bits. And in fact, we can simply extend this instruction to operate over the full 64-bit registers that correspond to its current operands. Now, this isn't enough to solve our problem, because if EAX is 0, then as I currently have it shown here, we'll still be subtracting by 0 through RAX, and we'll still have that fast path. But now that we have those upper 32 bits, we can pretty easily solve this problem by setting some of those bits in RAX, such that even if EAX by itself is 0, the whole RAX register will never be. And so we can safely run this subtraction without risking that fast path, and then twiddle some of those upper bits in RCX to come out with an answer that is semantically equivalent to what we would have seen in the original instruction. And it's also safe, because we've prevented any possibility that a computation simplification optimization will be applied due to EAX being 0. No, but this is just subtraction, and computation simplification is a broad class of optimizations. So we also transform, for example, 64-bit multiplication. You might notice this transform is much longer and more complicated than the one I showed you on the last slide for a couple reasons. One is that multiplication is especially hard, as many of you I'm sure are aware. Another is that as a 64-bit instruction, a lot of the trick that we used on the last slide doesn't work as is for 64-bit multiplication. And so we had to come up with different tricks that work for 64-bit multiplication, as well as other difficult cases of computation simplification. But among those different techniques that we came up with, altogether, we transform a broad set of instructions that could be subject to computation simplification under various cases that we compile from the prior literature. In particular, that Pandora paper that I showed earlier from Sanchez Vicarte et al. Is a main source for many of these optimizations for us. We also build transforms to address silent stores, which, as a reminder, is an optimization that can make memory stores faster when those stores are storing a value that already is at that destination in memory. And this includes not just instructions which store some register value directly to memory, but any instruction which uses a memory address as its destination. As one consequence, many of our arithmetic instructions that can be subject to computation simplification actually also have variants which store directly into memory. In those cases, they're also vulnerable to a silent stores timing channel, and our transforms account for this. And as I mentioned earlier, we formally verify all of our transforms for both semantic equivalence and safety. So we have our defenses, but we still need a way to apply them to source code. For that, we built a tool that we call CO for countering instruction-centric optimizations. And CO starts with some source code, typically from a cryptographic library, as well as a high-level secret annotations file, which tells CO for each cryptographic function we consider, which arguments into that function are secret and need to be protected. This is important because we don't want to pay the cost of transforming any instruction that doesn't actually operate over secret data. And so providing these annotations lets CO only transform those instructions that really need to be defended. CO will start by compiling that source code as normal to produce a binary file that will then be fed into our checkers along with those secret annotations. This is a set of program analysis tools that we built that will use those annotations to identify which instructions in that binary file are potentially leaky. That list of leaky instructions will then be taken in by our mitigation stage, which will recompile the original source code, but use our custom LLVM passes to transform those leaky instructions and produce a mitigated binary file, which can be run safely without fear of the timing channels that we consider. We evaluate CO on Libsodium, a widely used open source cryptographic library. And to do this, we handwrote secret annotations for the various Libsodium primitives that we consider. We evaluate first on build time, and we find that the checking and mitigation phases added by CO add about 12 minutes to the build time for a total of 3 times overhead compared to compiling Libsodium normally. And I'll note that this is a cost that you would only pay once when deploying the mitigated binary file. We also, of course, measure runtime overhead, looking at micro benchmarks to measure the performance impacts on the primitives that we consider. So looking at this chart that shows silent stores overhead, along the x-axis, you'll find each of the cryptographic functions that we look at in our evaluation. And on the y-axis is the normalized overhead versus a baseline without our mitigations applied. For silent stores, we found overheads varying from about 1.85 times to about 3.76 times, depending on the primitive. And much of that variance comes because different primitives use these vulnerable instructions at different rates. And so the more instructions a primitive has that need to be transformed, the more performance impact you'll see on that primitive. And this will be a running theme in our performance evaluation. We also look at computation simplification, starting with the set of transforms that can be applied to H to 32-bit instructions, excluding LEA instructions, which we look at separately. We also separately examine vector instructions, principally vector addition, and we look at 64-bit instructions, excluding both multiplication and LEA. You'll notice a big spike of performance on these 64-bit transforms, in large part because those transforms were just much more complex than the sets that showed up on this chart previously. Last but not least, we have 64-bit multiplication, which is, of course, by far our highest impact set of transforms, due again to that high complexity that those transforms require. Okay, so I'm sure you've noticed these overheads are really high. So why would anyone ever actually use CO? For one thing, better solutions like those in microcode might not be available yet, and you can use CO as a defense until they become available. Second, you would typically only need a small subset of these transforms. In practice, any given system is only going to implement some of these optimizations, and you would only use those transforms that are specifically relevant to your system. Finally, the mitigated code is only a small part of a larger program. I did call them micro benchmarks for a reason. In practice, these performance costs would only be paid on those few critical operations that really need constant time guarantees, leaving the rest of your code unaffected by CO's performance costs. In summary, we developed instruction-centric transforms as a general mitigation strategy against instruction-centric timing channels. And while the transforms themselves are specifically tailored to each optimization case we consider, the strategy as a whole is generally applicable, as shown by our applying it to this broad set of different computation simplification cases as well as silent stores. And we believe that it is also extensible to other instruction-centric timing channels. We implemented our strategy in our tool CO, which can act as a backstop when better defenses against these timing channels are not yet available. CO is available online at the Counter Optimization Organization on GitHub. Thank you.
Thank you, Alexandra, for this really great presentation. Now we can take some questions. We have a little bit of time. Any questions for the presenter? Yes, please.
Yeah, thank you for the talk. Do you have any idea how would CO prevent like speculative execution attacks, specter attacks? Because specter attacks are usually divided into two parts, like accessing a secret and then leaking it. I think from what I understand, CO would be preventing the second part. Is that correct? Or would it be preventing which part of it?
So CO is not specifically addressing speculative execution. In fact, it looks at optimizations that are applied non-speculatively primarily. So those computation simplification and silent store cases that we were looking at would generally be applied based on operand values, not necessarily speculation. Now, I could imagine a scenario where a system sort of predicts that an operand value might have these potential special cases and then tries to do the optimization speculatively, but our transforms would still protect against that because they're actually embedded into the binary code at the time that speculation occurs.
Okay, that makes sense. I might talk with you offline a little about this, but thank you.
Yeah, I look forward to it.
Hi, thank you for the great talk. Jonas Theograt. How did you come up with the transformation for multiplication? Was it just really hard thinking or?
It was really hard thinking and a lot of whiteboard time. I'm happy to talk more about it offline, but at a high level, we used a technique that we call split and recombine, which you can read about in our paper, which involves sort of splitting the different operands into the instruction into two or more different registers and sort of doing the operation in parallel on each set of split up operands and then recombining them with some clever arithmetic.
Thank you.
All right, thank you for the questions. Let's give a round of applause to Alexandra for this great work. Our next presenter is Zhao. I hope I didn't butcher your name. He will be presenting last level cache side channel attacks are feasible in the modern public cloud. To briefly introduce him, he is a fifth-year PhD candidate in CS at UIUC, advised by Josep Torrellas. His research focuses on computer architecture with a particular emphasis on system security. Specifically, he investigates microarchitectural side channel vulnerabilities in existing hardware, and he studies both the theory and the practice of building high-performance side channel defenses. All right, the stage is yours.
Okay, thank you very much for the introduction. I'm very happy to be here to present our paper on last level cache side channel attacks are feasible in the modern public cloud. So on modern processors, the last level cache or ARC is shared among processor cores. As a result, in a public cloud environment, if the attacker and the victim are running on the same machine, the attacker can exploit the shared ARC to extract information from the victim using prime and probe attack. However, despite the threat, cloud vendors claim that these attacks are impractical. For example, AWS claimed that in their white paper saying that these attacks are impractical due to the noise, therefore no mitigations are required. Indeed, modern cloud is very noisy. Besides attacker and the victim, there are many others users running there, creating tons of noise. Additionally, modern clouds such as function and service, they are very dynamic. User workloads can only run for a small amount of time before they are terminated, so the entire attack has to finish within a short time window. So to overcome these challenges, in this work, we developed a series of attack techniques that can overcome these challenges and eventually demonstrate cross-tenant information leakage with ARC prime and probe attack in production Google Cloud. Here are our technical contributions. First, we have a way to speed up the ARC channels setup, reducing the time required from more than 10 hours to only about 2.4 minutes. And we also have techniques that can monitor the victim and extract information from the victim in a noisy environment of the cloud. After reporting to Google, they filed a critical level bug report to their product team, and AWS revised their white paper. So before diving into more details, I need to first introduce our threat model and our assumptions. Generally speaking, before you can perform ARC prime and probe attack, the attacker has to first find a way to achieve co-location with the victim, namely they are running on the same machine. Because I have presented that how attacker can achieve co-location in the modern cloud this morning, I'm going to assume that the co-location step has already been achieved. Next, I'm going to assume that the victim is running during the attack. This can because the victim is running as a public web service that can be invoked by other users. Finally, I'm going to assume that the attacker is unprivileged, but has prior knowledge of the victim's cache access behavior. This can because the victim is running some publicly accessible program, so attacker can download it and study its behavior. So with these assumptions in our mind, let me walk you through a very quick background introduction to how ARC prime and probe attack works. From a high level, the core primitive of such an attack is called an eviction set. Basically, it's a set of cache lines that can fully occupy a cache set. For example, here on the attacker side, we have lines A1 to A4, and all these 4 lines form an eviction set for set number 1. Using an eviction set, we can monitor memory accesses to a single ARC set using prime and probe attack. The idea here is that you can load every single line from the eviction set to fully occupy set number 1, an action known as prime. Then you reload every single line back and time how much time it takes to reload, an action known as probe. In this case, because all the probe accesses are going to hit in the cache, you're going to observe a low latency of probing. In the future, if the victim accesses set 1, then one of the attacker's lines will be evicted. As a result, when you probe again, you are going to suffer from cache misses and observe a high reload latency. From there, you know that set 1 has been accessed by the victim. So the high-level takeaway here is that we need to build an eviction set and use that to monitor memory accesses to a single ARC set. However, in practice, there are so many ARC sets in the system, and only a few of ARC sets are accessed by the victim in a secret-dependent manner. We call them the target sets. And as an unprivileged attacker, we do not know where the target sets are. As a result, to actually perform these attacks in the cloud, the attacker has to start by building many eviction sets, such that you are going to have an eviction set for every LLC set in the system. For the CPU that we targeted in Google Cloud, that requires us to build about 57,000 eviction sets, which is a lot. After building all these eviction sets, you have to find out which one corresponds to the set you should monitor, corresponds to the target set. To do that, the attacker has to collect a short memory access trace from each LLC set and check whether that trace matches our expectation. In this case, it will scan through each cache set and find out that the set 1 is the target set we should monitor. This process is similar to how you tune a radio, try to find out which channel you want to listen to. After finding the set 1 is the target set, we can just monitor it and extract information from the victim. And this slide summarizes all the steps and all the challenges. And for this work, we propose techniques that can address challenges in each attack step. And eventually, we demonstrated end-to-end attack in Google Cloud. Now, because this entire attack is a very long story with many technical details, I'm going to mainly focus on the step of building eviction sets. From a high level, our contributions on building eviction sets is that we can speed up the process to finish it only about 2.4 minutes on average in production Google Cloud, while existing approaches can take more than 10 hours to complete due to the noise in the cloud, which exceeds how much time you can execute in the Google Cloud environment. To understand how we can make such huge improvement, I must introduce another piece of background about how to construct an eviction set. Suppose here we're trying to construct an eviction set for set number 1. To do that, we start by allocating a large set of virtual addresses that might be mapped to set number 1. Here, and we call that the candidate set. Here, the candidate set contains 10 addresses, and 4 of them are actually mapped to set number 1. We call these 4 addresses the congruent addresses. Then, after that, we have to prune down the candidate set such that it only contains congruent addresses. To do that, here's one approach. You can try to withhold a small group of lines like VA1 and VA2 away from the candidate set. Then you traverse the remaining addresses to see whether they can evict an attacker accessible target address that we know is mapped to set number 1. In this case, we should not be able to evict it because we only have 3 congruent addresses left in the candidate set. As a result, we know that the lines we withhold must contain some congruent address, so we should put them back. Then you can try to withhold a different group of lines, like VA9 and VA2 and VA10 here. In this case, after withholding, we can still evict the target, so we know that the lines we withheld must be not congruent, so it's safe to discard them away. After repeating this process multiple times with different group sizes, you can remove all the non-congruent addresses and form an eviction set. And according to prior work, this process takes about O(W²) memory accesses, where n is the size of the candidate set and W is the associativity. Now, in this work, what we found is that this process is quite vulnerable to noise, especially the parts that you are doing the test eviction. To understand why, we can consider this example. In theory, we should not be able to evict target, but in practice, while we are traversing all these addresses, there can be another noisy access made by a different container that accidentally goes into set number 1 and evicts our target by mistake. As a result, we are going to falsely believe that the 2 lines we withhold are not congruent, and we are going to remove them by mistake, which can result in the failure of constructing an eviction set, and that's why existing approaches often fail in the cloud. And in the paper, we also discussed a different algorithm called prime scope, which is similarly susceptible to noise, and our paper also provides more detailed quantitative analysis of both algorithms. Now, to improve the situation, we made a new technique, which is a new way to prune down the eviction set, the candidate set, with fewer test eviction executions. So here I'm going to give you a very quick intuition of how the algorithm works. Suppose that we're trying to traverse the first n at n=6 addresses to see whether it can evict target. We are going to find out that it cannot. So then we can try to increment n 1 by 1. With n=7, we cannot evict target. With n=8, we certainly can. So there exists a tipping point such that when n is smaller than tipping point, we cannot evict target. But when n is greater than or equal to the tipping point, we always can. The reason why this is important is because the line at the tipping point must be a congruent address. So here the idea is that we are trying to find where the tipping point is and use that to identify a congruent address. And if you repeat that process again, you can find enough congruent addresses to form an eviction set. Now the problem is that incrementing n 1 by 1 is not efficient. can we speed up the process? Well, here's an interesting insight. For a given value of n, if you can evict target, then it means that n is greater than or equal to the tipping point. Otherwise, n is smaller than tipping point. So given this insight, we can actually speed up the process with a good old binary search. Here's a very quick demonstration of how it works. Just like any binary search, we have lower bound and upper bound. We start from the middle. Here, we cannot evict target, so we update the lower bound. Here, and with n equals 7, we cannot evict target, so we update the lower bound again. Now with n equals 8, we can evict target, so we update the upper bound. Now, as the upper bound and lower bound are about to meet, we just found a congruent address, and we can swap that to the front. Then you can repeat the whole binary search process again and find the second congruent address and swap. And after 4 iterations of this binary search, the first 4 addresses from the list can form an eviction set for set number 1. And for this algorithm, it requires about OWN log n memory accesses. And compared to prior approaches, which one is faster actually depends on the exact value of n and w. But here I'm going to give you a quick intuition of why our algorithms is often faster, because our modern processors, the lateral cache usually have like high associativity, and we also have another optimization that can reduce the n before you run this pruning algorithm. So now I must leave you at this cliffhanger of what's happening next, but I can give you a very quick summary of the insight. So to find the target set, our insight is that the victim accesses to the target set are often periodic. So you can process the access trace you gathered in the frequency domain via spectral analysis to find out which set is the target set. And for the step of extracting information, our insight here is that you can overlap memory accesses of prime and probe accesses to exploit the memory level parallelism, and that can reduce the latency of doing prime and probe, and that can improve the resolution of the attack. And after overcoming all these challenges, we were able to demonstrate end-to-end attack in production Google Cloud. And the target victim that we used was a ECDSA, a vulnerable ECDSA from an old version of OpenSCL. Here, I want to say that this version is known to be vulnerable, and we are not claiming contribution here. But nevertheless, on average, we can extract an average number of 68% of the secret nonce, or a median value of 81%. So now to summarize, basically, in this paper, we demonstrated cross-tenant information leakage in production Google Cloud. We have methods that can speed up ARC channel setup and techniques that can monitor the victim and extract information in a noisy environment. And after reporting to Google, they filed a critical level bug report internally, and AWS revised their white paper. So, and also here's our open source release on GitHub. So that's the whole talk. Thank you.
Thank you for the great presentation. Do we have any questions? We can have 1, at most 2 questions.
I did not try Azure, but I think there's nothing fundamental to Google Cloud, because all it takes is just we tried Intel CPU with non-inclusive ARC, and it works. For Azure, I do not see any reason why it cannot work.
All right, then let's give a round of applause to our presenter. Thank you so much. Our next presenter is Hussein. He will be presenting Pathfinder, high-resolution control flow attacks, exploiting the conditional branch predictor. Hussein is a third-year PhD student in CS at UC San Diego, advised by Dean Tolson. His research focused on computer architecture, security, particularly novel side channel attacks, and high-performance mitigation like control flow isolation. The stage is yours, Hussein.
Thank you so much for the introduction. I'm Hussein. Today, I'll be presenting Pathfinder, where we introduce 2 novel side channel attacks exploiting the conditional branch predictor. This is in collaboration with a bunch of folks, as you can see here, from different universities and industry. So let's get to it. Conditional branch predictor has been the target of many attacks, including Spectre, branch scope, branch spec, and many others. And previous attacks actually lacked knowledge of the exact structure of the CBP. So specifically, they didn't know much about the global predictor, which has the highest accuracy, and is used more within the branch predictor. So they use methods like brute forcing to cause the branch to mispredict, which resulted in low resolution poisoning attacks and leaking only the biased direction of a single branch. So in our prior work called half and half, we reverse engineered the intricate details of the branch predictor, including the every single table, indexing and tagging hash functions, every single thing within the branch predictor. And in this work, building upon that, we introduced two novel side channel attacks. The first one is about recovering the almost entire runtime control flow of any victim program, which enables us to extract complete local history of any single branch instruction, recover the complete global history of any victim program, and the precise ordering of the executed instructions. And the second attack is an extremely high resolution spectre style attack, which enables us to poison any specific instance of a conditional branch within the branch predictor. So let's get to a little bit of background about the conditional branch predictor. So in half and half, we found that in modern Intel processors, conditional branch predictor has a Tage-like structure in the sense of having a local predictor, which is indexed by the PC or the branch address, and the global predictor, which has three tables, each of which is four-based associative, which is indexed and tagged by a combination of branch address and global history. So the main difference between this branch predictor and Tage-like branch predictors is the global history. So we know that in the literature, global history is in the form of global history register or GHR. So this shift register is updated based on the direction of conditional branches. Whenever a branch is taken, you insert 1. Whenever it's not taken, you insert 0. But we found in modern Intel processors, so the global history is actually in the form of path history register or PHR. So the main difference between PHR and GHR is that it's only updated based on taken branches of all types. And that is updated based on the branch address and also the target address. So for example, in Raptor Lake processor, we found 16 lower bits of the branch address and 6 lower bits of the target address are combined in this way to make a footprint. And every time a branch is taken, we shift this shift register by 2 bits to the left and then XOR the lower bits with the footprint. We call this 2-bit thing as a doublet. But the most important thing about the PHR is it not only keeps track of the order of taken branches, but also their addresses, not only the branch address, but also the target address. Now that we know everything about the PHR, let's talk about some basic primitives to manipulate the PHR value. So first of all, we created a primitive that you can shift the PHR value. Let's say this is the value of PHR before executing the shift PHR, and after executing that, you just shift this PHR value to the left by amount that you want to. So another primitive, clear PHR, as it sounds, it's just gonna clear the entire thing. And the most complicated one is called write PHR. With this primitive, you can control any single bit within the PHR and set it to any specific value you want to. For example, you can set it to a very specific value, a set of zeros and ones within that. But the thing is, we created a tool to read this value of the PHR. But let's first talk about why that can be important. So let's say this is the victim code, and after executing the victim code, we get this PHR value. You can think about this PHR value such that P0 has information about last branch history, P1 has information about second last branch history, P2 has information about the third last branch history, and if you find a way to read the PHR, you'll know what happened exactly within the victim code. Now I'll talk about how to read the PHR. Before diving into the details of that, let's consider this very simple example. Let's say we have 2 conditional branches right after each other, and both of them are conditional branches based on a very specific condition, which is a random bit, true or false. So this is a very hard to predict branch. So, but these branches correlated, which means when the first one is taken, the second one is taken. When the first one is not taken, the second one is not taken. When we measure the branch misprediction rate for the second branch, we see it's 0%. But the question here is how the branch predictor can predict the second one based on the first one. So the thing is, when the first branch is taken, as I told earlier, PHR only gets updated per taken branches. When the first one is taken, we update the PHR. So in taken path, it's going to be PHR 0. When it's not taken, it's going to have a different value, PHR of 1. Since we have two different PHR values in two different directions, branch predictor will be able to predict in that way. Now let's assume we have a sort of tool to compare PHR values. Now let's talk about how do we read bit number 0 of the history within the PHR. Again, we have the simple example, but we're going to do some specific actions within each path. Let's say in the taken path, I'm going to first clear the PHR. So every single bit within the PHR is 0. Then I'm going to call victim. And let's say victim returns me this PHR value that I want to read. But in this step, I just want to read P0. In order to do that, and in order to isolate the effect of P0, I'm going to shift it such that P0 is in the most significant bit. All the other bits are 0. In the not taken path, using write PHR, I'm going to write a very specific value, and that very specific value is that I have an X in the most significant doublet, and all the other bits are 0. And this X is the value that I will be brute forcing. When X is equal to P0, misprediction rate will be 100%. Otherwise, it will be 0%. By brute forcing X, I'll find out what was P0. I can go ahead and find P1 right now. I again clear PHR. I call victim. Right now, I want to read P1. I'm going to shift such that P1 right now is in the most significant bit. In the other path, I'm going to set it to X, P0, all the other bits 0. And again, brute forcing X. When X is equal to P1, misprediction rate will be 100%, and I'll find out P1. I can continue this and read the entire value of the PHR. But the problem of that is that PHR has a very limited size. In some processors, like older processors, it's 93, and the new processor is 194. So you can just read that value. So we created a tool called extended read PHR. And this extended read PHR actually helps us to read the entire PHR value of the victim program. Now, let's think about this victim program, which does have more than 194 branches. So the PHR value right after the victim has information from the last 194 taken branches, or actually from the green ones. We don't have any history of the red branches here. But the thing is, in order to predict a branch within the victim, we'll look at the history of last 194 branches from the point of view of that branch. So in order to predict the last branch within the victim, we look at the history, a window of last 194 taken branches from that. As you can see here, it includes one more bit of history. So we can use that to make some collisions within the prediction tables to read one more bit of history. And you can continue this to read 2 more bits of history, 3 more bits of history, and you can go as far as the entrance of the victim code. So right now we know how to read the PHR, but PHR is a bunch of zeros and ones. And what does that value mean? So we created this tool called Pathfinder. It's a Python tool. You give it the PHR value to it, and you give it the binary, and it gives you a control flow graph of the victim code, which marks the executed path that actually victim got executed in that. This actually gonna tell you what branches were taken, what branches were not taken, how many iterations a loop got executed, and all those sort of information. So we show that we can actually, by that information, attack libjpeg. So there's this is so funny in IDCT. IDCT is inverse discrete cosine transform function. We found actually a secret dependent branch. So there is an optimization which checks if all the members of a row and column within a matrix that's getting processed by this libjpeg library, if all of them are zeros, we're going to do simple computation. Otherwise, we're going to do complex computation. And now let's say by reading the PHR and extracting which rows and columns are constant or 0, we can reconstruct images. For example, this is the original image, QR code that points to the ASPLOS webpage. We get this, which includes all the edges of the image. And by doing a very simple algorithm, applying a very simple coloring algorithm, you can recover this image, which is scannable. So these are other images that we recovered, ASPLOS logo and the background image. So in addition to reading PHR and writing PHR, we show that by knowing that information, we can actually write and read the prediction tables as well. So which means that we can poison any specific entry within the branch predictor, and also the leak the value of that entry. So this enables us to do very high precision spectre style attacks, poisoning attacks. And for example, in previous attacks, we wanted to mispredict a single branch. For example, if a statement which checks if X is, for example, less than condition, and then we want to mispredict this as true instead of false and doing some speculative execution, a very simple example of a spectre V1. But with our attack, we can introduce complicated patterns of misprediction. For example, we can cause a misprediction in the nth iteration of a loop, which can cause exit earlier speculatively, causing underlooping or even overlooping. And also we can cause much more complicated patterns of misprediction. For example, let's say you have an if statement within a loop. You can cause, for example, in 80th iteration of the loop, this branch gets mispredicted. So we show that with this, we can leak AES key. For example, consider this looped implementation of AES, which we do, which the number of iterations for the encryption decryption is implemented by a loop. What we do is we cause this loop to speculatively, for example, after the first iteration. And by doing that, and by getting the reduced round ciphertext with the speculative execution and comparing that with the normal execution, we can extract the AES key. Yeah, thanks for your attention. I'm happy to take the questions.
Thank you. Very interesting work. We have time to have some questions. Any question?
Hi, great talk. If I understood it correctly, you have to run the program multiple times to get the whole path right. How often did you have to run, for example, the lib-JPEG thing to execute to extract images?
That's right. So first of all, for example, in complex photos like QR code, we managed to go back up to like 20,000 branches. But I would say for each bit of the PHR, you have to call it 10 times. So you can calculate that.
Okay, thanks.
Any other questions? I can ask one question. So how about the defense side? So for instance, IBPP, does it flash this register? How would you, did you contact Intel? What is their response to this attack?
Yeah, so first of all, we checked all the other Intel mitigations like IBPB, IBRS, STIBP. None of them deals with conditional branch predictor, specifically with PHR. They don't flush the PHR, even the prediction tables. But the most efficient mitigation for read PHR would be flushing it like within a context switches between the attacker and the victim. And for the primitives targeting the prediction tables, you would have some sort of isolation between the attacker and the victim. What we did in half and half was actually isolating the branch predictor into two parts. So the attacker and victim are not going to share the same entries within the prediction tables.
I see. How about the Intel's response? Like, did you contact them? What
yes.
was?
We contacted Intel and AMD. Their immediate response was to, for the poisoning attack, was to use the measures for spectre V1, which means using the fences after the branches. But for the other ones, secret dependent ones, is like to use constant time programming, which the very high-end like libraries, it's not used.
All right, thank you. Any other question? All right, then let's give a big round of applause to our presenters. Our next presenter is Flanders. He's a PhD student at Stanford University, advised by Professor John Osterhout and Kent Winston, working on network interface card architecture. Previously, he completed his BS and MS degree at UCSD under the advisement of Professor Ryan Kastner and Dustin Richmond, which is the work he will be presenting today. All right, the stage is yours.
Thanks. Hi, my name is Colin Drews. I'm a PhD student at Stanford University, and your transistors are leaking your secrets. Your computer's transistors hold your secret values. Transistor switching time changes as a result of those held values. These timing deviations are persistent and measurable. Measure the timing, recover your secret. Now let's talk about art. A pentimento in art is the presence or reemergence of early images which have since been painted over. On the left side here, we have Rembrandt's An Old Man in Military Costume. When we examine that under sophisticated X-ray scanning techniques, we reveal a previous image that the artist painted over. Now we're interested in a phenomenon which we call a digital pentimento, which is the reemergence of digital data that has since been overwritten. Now, why do digital pentimento crop up in real hardware? Well, as digital designers, we have very idealized views of the hardware we build and design with. On the left side here, we have an inverter composed of a PMOS and NMOS transistor. But of course, transistors are not atomic elements, and there's a great deal of underlying complexity. In particular, transistors are vulnerable to a class of degradation effects called bias temperature instability. Under bias temperature instability, as a transistor is exposed to stress, being voltage and temperature, its switching speed begins to change. And the effect of this is to create value-dependent timing deviations in the behavior of that circuit, in this case, an inverter. So for example, if the input to this inverter, Vin, is held at a 0 value for a long enough period of time, as the PMOS transistor propagates a 1 value, the negative bias temperature instability effect will begin to manifest. This will affect the switching speed of the transistor. And as a result, as an input, Vin, goes from 1 to 0, and the output goes from low to high, the amount of time it takes for that propagation to occur, or TPLH, will begin to slow. Now, there's also a complementary effect for NMOS transistors called positive bias temperature instability effect. And as the input to the inverter is held at a 1 value, the positive bias temperature instability effect will begin to accumulate, slowing the switching speed as the input goes from 0 to 1 and the output goes from high to low. Now, we express both negative and positive bias temperature instability with a single value called delta PS, which is just the difference in the propagation time as the output goes from high to low minus low to high. And so if you can precisely measure the timing through digital components or this delta PS value, you can determine the previous logical value which they held. Well, we can measure the timing through the programmable routing of field programmable gate arrays. Programmable routing is the primitive unit of interconnect used within FPGAs. And we can do this using a self-test sensor that can be remotely programmed into the device itself. Now, we devise an experiment to test this hypothesis. We do this in a local controlled lab environment in an oven. We place the FPGA in an oven holding the temperature constant at 60 degrees Celsius. We generate a set of artificial routes of varying lengths, which we place onto the FPGA. Our experiment is then divided into 2 phases, a burn-in phase and a recovery phase. In the burn-in phase, we generate a random bit vector X, and we load that into our artificially generated programmable routes. We let that value X sit in the routes for the majority of an hour, at which point we perform a measurement where we capture the delta PS value. We do this 200 times for 200 hours of data and 200 data points. We then begin the recovery phase, which is identical, except instead of loading X into the routes, we load X complement, the opposite. The goal here is to test what happens when you de-stress a route. Does it return to its nominal operating timing behavior, or do these effects persist? Again, we get 200 data points for 200 hours of data from that portion of the experiment. Now we plot the delta PS values captured throughout this experiment, which are again our measure of this bias temperature instability effect, against hours to see how the BTI effect compounds over time. Now what we'd expect to see is that the routes which hold a 1 value will have some positive or negative delta PS value, and the routes which hold a 0 value will have the opposite effect. And our local data backs this up. We immediately see that routes which hold a 1 value, or magenta, have a positive plus 10 picosecond delta PS value, whereas routes which hold a 0 value have a negative 10 delta PS value. Another thing we hope to see from this was that the magnitude of the observable bias temperature instability effect would depend on the length of the route. This is intuitive because the longer a route is, the more transistors you have in a chain, and the more you expect the BTI effect to compound. And again, our local data validated that hypothesis, where long routes experienced 10 picoseconds of delta PS change, whereas short routes, only 1,000 picosecond in length, experience just plus or minus 1 delta PS. Finally, we expect to see that the bias temperature instability effect has some elasticity. When you remove that stress, the timing behavior of those programmable routes will return to their nominal value. And what we see is, yes, they do return over time to their nominal timing behavior, but it's different between routes which previously held a 1 in the burn-in phase versus routes which held a 0 in the burn-in phase, the burn-in phase being the first 200 hours. We believe this is a fundamental difference between the positive and negative bias temperature instability effect. Now, here's how an attacker can exploit that information to design a cloud FPGA threat. We assume that some victim user rents an FPGA from one of the major cloud providers, and they load their design onto the FPGA. This design contains some sensitive value. It could be design data if it's a constant that's baked into the bit stream itself, or it could be runtime data if it's like a key memory that is initialized when the user programs after the user programs the FPGA. Now, this victim user allows their computation to run on the device for a number of hours, long enough so that the bias temperature instability effects have begun to form on that sensitive data. After those BTI effects have accumulated, they give the device back to the cloud provider as they're done with their computation. Now, the cloud provider, being very eager to release this device to the next user as quickly as possible, leases it to the next user. But this user is an attacker, and they program onto the FPGA fully remotely a self-test sensor to measure the delta PS values through the routes which previously held the sensitive data in the victim's design. Using those delta PS values, they recover the initial values, bit values of that sensitive secret data. Now, in order to validate this hypothesis, we design an experiment that follows very closely to our local experiment. The major differences are, first, that we're doing this in real live AWS data centers in the EU West and EU Central regions. Instead of testing artificial routes, we're testing a highly parallel AES core that has a single key memory. That key memory distributes its key value through programmable routing to the remainder of the design. Instead of loading some random bit vector X into the routes, we initialize the key memory with a key value that's going to be used for the computation. In the burn-in phase, we again interleave letting this value sit in the routes, the key, with occasional measurements of the delta PS value. We do this 48 times for 48 data points over a 24-hour period. We then perform a reboot phase, where we give the FPGA back to the cloud provider, and they perform whatever proprietary wiping they want to perform, and then we release the device from the cloud provider. Then we begin the recovery phase, which is again similar, except we're loading a 0 value into the key memory. We're loading a 0 value here because we're trying to look at this from the perspective of the attacker. Of course, the attacker can't load key complement into the route, so they're just going to initialize all the routes with a 0 value and study that bias temperature instability recovery. Based on the magnitude of the recovery, they can determine what the previous value was. Again, we interleave letting 0 sit in the routes with occasional measurement of the delta PS values. What we're really testing here is 2 threat models. The first threat model being some constant is baked into the bit stream itself. These bit streams are encrypted. And an attacker is then able to interleave measurement with letting that encrypted bit stream design sit on the FPGA. And we're also testing here a runtime data threat. So if an attacker comes onto the FPGA after some victim user has been computing on that device for a number of hours, they can recover dynamic data that was loaded onto that FPGA that is now gone. Now, in order to validate how well an attacker can actually exploit this threat model, we perform a key recovery attack. The first step in this key recovery attack is to feed the data that we capture throughout this experiment, the delta PS values, into a k-medoid cluster. The k-medoid cluster is just trying to group the data points into 2 groups. One group corresponding to bit value 0 and the other group corresponding to a bit value 1. We then plot the accuracy of this k-medoid cluster over time. And we see for the first threat model, the design constant key recovery, there's a high 90 to 100% accuracy clustering between 2 groups just based on that delta PS value. There's a clear an observable difference in the timing behavior of programmable routes just based on the previous value that they were holding. Using confidence values that were generated from this k-medoid clustering, we're able to perform a full key recovery in less than 1 second for 5 out of the 8 boards. Under our second threat model, we progress very similarly. We feed the data into our k-medoid cluster. This is just the recovery data, where an attacker has come onto the FPGA after a victim has relinquished it. They load a 0 value into all of the routes and just study the recovery from BTI over time. Again, we see just feeding this recovery data into our k-medoid cluster that the accuracy is extremely high, 80 to 90% accuracy, able to separate routes into a group corresponding to a 0-bit and a group corresponding to a 1-bit just based on the delta PS values. We're however, unable to perform a full key recovery due to a few high confidence outliers, but we view this as just a methodological problem with a simple resolution. Anything above 50% in this k-medoid clustering accuracy is cause for great concern because it indicates that there are persistent value-dependent timing deviations that occur and exist between FPGA restarts in live cloud AWS FPGA environments. So what can you do to protect yourself against this? Well, we've sort of thought of a grab bag of different tricks that fall into roughly 3 categories. First, what can you as a user do? Which can be obvious things like don't leave long-term static data sitting on your FPGA. That's the best way to mitigate the burn-in effect. There are things that the provider can do for you, like implement launch rate controls. Maybe when you give your device back to a cloud provider, they shouldn't eagerly lease it to the next user. Then there's things that the manufacturer can do, like increase the size of the transistor node to reduce its vulnerability to bias temperature instability. That one's a little more far-fetched. In conclusion, this differential is a little scary. There's a clear and observable timing difference between any circuit that holds a 0 value versus a 1 value, and it's observable in real live data center environments on cloud FPGAs. I'd like to thank my collaborators, Andy Mesa, Olivia Wang, Ryan Kastner, Dustin Richmond, and David Kohlbrenner. Thank you very much.
Thank you for this awesome presentation. We have a couple of minutes for questions. Any question from the audience? Okay.
Hi, excellent talk. I wasn't quite sure what you said you were recovering data in this burn-in phase as well, but what data are you recovering? It sounded like that's when you're running the victim program.
Yes, so we're considering 2 threat models here. The first one, when we're considering just this burn-in data, we're thinking of a scenario where the cloud provider like AWS has a marketplace of designs that contain proprietary information. So this is the current state of affairs. You can put your design onto the AWS marketplace, and AWS guarantees to you that the values you put in your bit stream to sell to people will be kept proprietary. So under that threat model, an attacker can interleave the measurement with letting your proprietary image with secret data sit on the device.
Makes perfect sense. Thank you.
Thanks.
Hi, thank you for the great talk. If I understood this correctly, you need to know where the key was stored. Is this correct?
That is correct, yes.
Are there any realistic scenarios where you know that? I just heard about the marketplace, so there you can probably get the model and then look at where the key is stored.
We think with the emerging prevalence of open source designs, even open source designs that you don't need to recompile to initialize with proprietary information, as a compelling threat model for this. So OpenTitan, for example, has a precompiled bitstream that you can then initialize with proprietary values. And of course, that encrypted bitstream, we can determine the routing of very easily because we have the entire end-to-end compilation flow.
Makes sense. Thank you.
All right, before we wrap up, I would like to thank you all of you for your amazing work and also all the audience who attended the session. For many of you who may not know me, I am Sadullah Canakci. It was honored for me to lead this session. I'm part of the security and virtualization team in AMD and really happy to be part of this session. Thank you again for all attending and then have a nice conference. Thank you.